I can give you just a few images of flowers and tell you like these first 5 are class A, the next 5 are class B, and the last 5 I will just call them class C. And by now you had the time to look at them. I can give you a new one and ask you what class is this, and I'm pretty sure almost all of you will answer correctly now already. Another one. These are very different images, satellite images that you may rarely see in your life actually, but still I'm going to give you 5 and call them class A. 5 other ones, call them class B, and 5 other ones, call them class C, and then again show you one. This is maybe a little bit less trivial than the previous one, but I've talked a lot. By now you know which class this is already. And the last one, a bit more abstract. I'm going to give you here 6 examples of class A, 6 examples of class B, and I'm going to show you a new one. This, depending on like your prior thinking and so on, may require a little longer. So I'm going to give you like 5 more seconds. Dum, 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 dum. By now you've looked at this, looked at that, matched it, and I'm pretty sure most of you know what it is. If not, this is class A because it's only 3 objects and class B is 6. But as you have seen, your visual system is pretty good at picking up new tasks, very different tasks, with just a few examples. And this is because of what your visual system can already do. Like you see this image, you immediately see, yeah, there's a bunch of boxes, shadows, colors, different materials, and so on, right? You have a good preconceived vision system. And this is what we call, what we mean when we say general visual representation. You have a good one in your brain, and we're trying to do the same. So, okay, this is the goal. How do we measure progress towards it? A couple of years ago, my team and I, we did what we call the visual task adaptation benchmark, which provides the setting in which all of the following things I'm going to talk about live in. So there is this model that comes from somewhere you have trained somehow. I don't really care. Maybe it's on Hugging Face Hub and you can download it, or elsewhere and you can download it, but this model exists, right? And now I want to test this model. How close is it to general visual representation? Then there is this landscape of all reasonable visual tasks, and we propose to basically sample some. And so we sampled 19 of them, and each task comes with very few examples per class as a training set and a test set. And now you give me your model and you give me an adaptation algorithm, and I apply this to each task individually. Right? An adaptation algorithm does whatever on it wants on this little training set, and then makes predictions on the test set. And I compute the average score on the test set, and this is your models and adaptation algorithms VTAP score. And we posit that by making progress on this VTAP score, we make progress towards a general visual representation. So this is the setting and a little bit of nomenclature. This left side, what you do to prepare is called pre-training or sometimes upstream. And this right-hand side is called transfer or sometimes downstream. Right, so this is the setting we operate in and the goal we have. Now, how do we get there? Over the past few years, we thought a few ways to get there. Initially, we thought, self-supervised pre-training, that sounds really cool. There's like potentially infinite images out there. We could just train visual knowledge from there without any labels. Long story short, we did some progress on that, published some papers, but at the end of the day, we believe there's always need for some labels somehow. Like if you train a couple models, you need to choose one at the end of the day somehow. And you need labels for that. Or if you don't have labels, you look at what it predicts and say, yeah, this is good, this is bad, then boom, you just created labels. So then we looked at semi-supervised pre-training for a bit with few labels and a lot of unlabeled images. It also works reasonably well. But eventually we landed at large-scale supervised pre-training, where you pre-train on tons of images with some annotations. And this worked really well. And this set the ground for Vision Transformer afterwards. So I'm going to dive a bit more into this large-scale supervised pre-training, and then going to talk all about Vision Transformers. All right, so as I said, the images come from somewhere, and there is some information there that you can transform into a label. Even though it's not perfect, it can be a good enough label for learning. And at Google, we just happened to have this large data set lying around there of 300 million images from the web with some weak labels that were obtained through some process. And so we used that and looked at what can we get by pre-training models on there. And turns out that by pre-training in the right way on this huge data, we get huge wins. Like, let's not care about the details here, but basically state of the art across many vision tasks by pre-training a ResNet on this. But more surprisingly, we found one thing here. X-axis is larger model. So to the right, the model gets larger. And the different curves are pre-trained on different amounts of data, green being the least data and orange being the most data. And here's the first surprising, at least to us, finding that for this few-shot learning, which is the game I played with you before, the larger the model and the more data it was pre-trained on, the better it performed there. And especially like the largest model on most data was really good. Another thing was robustness. We evaluated many different ways for robustness, but this here is one example of ObjectNet, which is a data set like ImageNet, but much more in the wild, as you can see here, much more noisy, like chairs on beds and stuff like that. And same story here. The curves mean the same as previously. And the thing is, the largest model pre-trained on the most data is just ridiculously more robust than like common models trained on common size data. Without any extra tricks or anything. So this was really good news. And this set the ground to large-scale pre-training. Just gonna briefly, it sounds easy, right? Lots of data, big model, and that's it. So I'm gonna very briefly go through a couple little details on why it was actually not obvious at all to get there. One thing was InVision batch norm is very widespread because it's in ResNet 50 and ResNet style models, and they are very widespread. This is regular training and testing curves if you train ResNet 50 on ImageNet. Looks good. Throw in tons of data, like 100 times more data, and it looks like this. The test loss looks completely crap, and nothing works, and it's unstable. Turns out that after long searching, the culprit is batch norm, which has many issues. But basically, after some digging, we proposed to replace batch norm by group norm and weight standardization, and boom, we are back into the game. But it's not the focus of this talk why that is, and really why we don't know either. We just have some hypotheses. Another thing is that when you pre-train, you actually need patience when you pre-train on lots of data. Here, this dot is the starting point of standard training on ImageNet. Just using 10 times more data and not changing anything else looks like it's worse. But if you actually then train longer and longer and longer, then it gets better and better and better. Just to show you how kind of ridiculous this is. This is a training curve. This is my favorite plot ever. This is a training curve, and this is what it looks like if you look at the small section of 8 GPU weeks of training. That means 8 GPUs for a week or 8 weeks on single GPU. It looks flat. Any reasonable person would stop and say, yeah, this is it, we're done. But if you just are unreasonable and keep training and keep training and keep training, this is what the exact same curve looks like then after 8 GPU month. And if you look at this, you're seeing, yep, consistent progress. Let's keep going. And yeah, let's skip that in the interest of time. Another thing is that you need to scale both model and dataset size together. If you have this blue dot, which is ResNet 50, and you just train it on more images going to the right, it looks like it's getting better, even more images, and we're back to getting it worse. But if you, ResNet 101, the same, by the way, the green dot. But only when you get much bigger models, you keep seeing benefit for more and more data. So that means large model, lots of data. Once you did that, actually, I'm not going to go through details here, but once you did that in the pre-training, our transfer or fine-tuning is really simple. It's just take the pre-trained checkpoint, SGD momentum with a small learning rate, and you're done. Like no tricks, no weight decay, no residual adapters dropout, whatever. One trick, in a sense, that we use is from a Facebook paper. It's called FixRes, which is basically fine-tune at higher resolution. And they have lots of experiments and justifications and so on, but that works pretty well. Sometimes mix up. All right, so then we basically figured this out, how to do large-scale pre-training, and we got, this was the model we called BIT for big transfer. It was state-of-the-art on ImageNet. It was great. And then we were there, and we thought, okay, so now we know how to do large-scale pre-training. What next? And basically, InVision, convolution has been like the only name in town since forever, right? ConvNets everywhere. In language, that was the case with LSTMs or RNNs. until transformer came and completely changed everything. Convolutions seem to fit very well image data, and RNNs seem to fit very well sequential data. But then comes transformer, which doesn't really seem to fit sequential data better than RNNs, but actually transformer and large data completely outperformed RNNs in language. So we wondered, could this be the same? Could the same happen in vision? And that let me introduce you to vision transformer, which says yes. And the basic idea is super simple. I'm assuming that you already know transformers in language at least. In this case, you take the image, you cut it into patches, and each patch of the image basically becomes a word in the sentence. You just sequentially walk through the patches. Each patch is a word. You project them into their embedding space. You add the position embedding. You add the token for the class, like the end of sentence token in language. Then you throw all of this through a big transformer encoder, and then you extract from the class token a classifier and predict the class. And this transformer encoder is literally just exactly the language transformer from the original paper or from BERT. Even here, the layout, base and large are exactly the same as in BERT, base and large. And we also defined the huge, which is a bit larger. The only new thing is what is your patch size? And we denote this here with the /16. We usually take 16 pixels, sometimes 32. And then we do this whole thing that I talked about previously, this pre-training on large data and then transferring with this very simple transfer recipe. And you've seen such a plot just before with the this again, but with the vision transformer, and it looks to scale better. Because in language, this has been done a lot, scaling it up. And this works. It's on the later slide. It's got SOTA everywhere too. But then let's look a little bit closer at these position embeddings, because I told you we just take the patches, walk through them like through a sentence, and that's it. So we completely that they come in a 2D layout. And the position embeddings actually learn this by themselves where they are from. So here, each square on the grid is one position embedding, and then each pixel in that cell is how similar is it to these other position embeddings. And as you can see, the position embeddings, they recover this structure of the grid layout where they are from. They are most similar to position embeddings from nearby patches. We also did try like putting some 2D information in the position embeddings using relative position embeddings. They all basically perform the same. Doesn't matter. It just learns to recover positions. Just removing position embeddings still works, but worse. Another interesting thing is the receptive field size. Like if you have the self-attention, you can look how far does it attend to on average. And in the early layers of the network, we have some heads that attend very far, some heads that attend only locally around them. And this slowly disappears. And after about half of the model's depth, we only have attention heads that attend very far. So the model learns to first compute more locally and then later only globally, which is pretty cool. We just let it learn this from data. And yeah, like I said, then with this model, we got even better results on ImageNet again. And since, as I said, we know how to scale vision or transformers in general, like, okay, let's do it. Let's scale it even further. And that's how we're going to go to this with G on the right. And yeah, that was a recent paper of scaling up vision transformers. So how do we get there? Okay, first thing is to just get more data. This is a bit boring, more data better, but not that much if we don't change anything else. Now the question is how to scale up the model. And here we're going to talk a little bit about TPUs. You probably heard in the previous presentation, TPUs really like multiples of 128. And the title of the vision transformer paper was an image is worth 16 by 16 words. So 256 words. That's 2 times 128. That makes TPU very happy. However, I previously mentioned we add this class token, which learns like what is the class. And so in reality, we have 257 tokens there. That makes TPU pretty sad, and it just pets stuff left and right. And it's a waste. TPUs really don't like that. So can we get rid of this? That's what we looked at. And luckily, the answer is yes. This is actually completely unnecessary. But it was just from us being as similar as transformers in language. But turns out we can completely remove this extra token, just use global average pooling or global max pooling in the head. It just works. Or we can use a multi-head attention pooling, as was presented in, what was it? Set transformer paper, I think. And that works. They all work equally well, but the multi-head attention pooling is cool. We can imagine doing more things with it down the road. So we went for that one. And then we have 256 tokens actually, which is very nice for TPUs. Another thing is for scaling up. For scaling up, memory is the most important thing, or the most precious resource. So we try to save it where we can. And the vision transformers, we train it with Adam. And Adam Optimizer actually needs 3 times the model size total memory for the model parameters and twice for 2 different statistics for each parameter. That's way too much, basically. But like I said, we can always look at how do language folks scale up transformers. And there was other factor optimizer proposed, which only needs the model parameters in memory, then some very small overhead. However, if we just apply this to vision transformers, it simply doesn't work. So we had a little bit of time digging into it. We found that eventually we need to reintroduce the momentum term, but we can store it in half precision. We need to disable some automatic learning rate scaling that's part of Adafactor, and like a few such small tweaks, and then Adafactor works very nicely and matches the training curves of Adam almost perfectly, but with half the memory overhead. So great, we just cut our memory usage in half, means we can make the model larger. And now here's another thing about JAX and TPUs in general. It's a compiler, so it compiles your model and it has lots of optimization passes, which try really hard to let your model run. So they try to do automatic gradient checkpointing and things like that to save memory if you ask it to run a large model. So that means you can barely predict if the model will fit or not. Even if you look at the free memory, you might fit more than what was free before. So basically what we do is run lots of vision transformers in lots of different settings. Here we have each square is one model setting. Then we have the width of the MLP, the number of layers across the plots, and the width of the self-attention on the height. And a color means it fits. Orange means the original vision transformer paper setting. And here I marked the layout of with L and with H from the original paper. And then in green and in blue, with the memory saving improvements that I talked about earlier, we can fit a lot more. And so we select some model here, not completely arbitrarily, but more or less on gut feeling. We know that we need to scale everything a bit and run this as the largest model. You can see some holes here. These are not bugs. These are actual situations where the compiler manages to fit a larger model, but not the smaller one. That happens sometimes. Basically, to know what fits, you actually need to try to run it with JAX and TPUs. All right, let me skip this. It's pretty cool, but in the interest of time. Another thing we noticed there or introduced is you can get a lot of win on few-shot learning on this VTOP setting that I told you earlier. If you sacrifice a bit of the pre-training performance or upstream performance, as we say here, by using different weight decay for the head than for the rest of the model. So apply large weight decay for the head and small weight decay for the rest of the model. This makes your pre-training performance look worse. So you might think you have a worse model, but actually the representation that it learns is better and it performs much better in few-shot learning. The intuition behind this is if you think back at SVMs. In SVM, you add the weight decay in order to increase the margin between the classes. And we believe there's similar thing going on here. If we have a high weight decay on the head, we ask the representation that comes into the head to have a larger margin. And this larger margin then makes eventually few-shot learning work better. All right, taking all of these things together, we get a really good vision transformer model. This is with G, this giant model that I showed you with all of these tricks. This dotted line is the previous vision transformer from the original vision transformer paper. And here we have another couple popular models that are pretty good at few-shot, which is SimClear and Beyer. These are 2 self-supervised methods. And it is actually pretty amazing. With just 10 examples per class on ImageNet, this VG gets 85% top-on accuracy with just a linear classifier on top and just doing linear regression, nothing else. Yeah, so this is cool. However, a few more things are cooler than the SOTA, I think, or a few more insights here. The first one, these three plots are essentially the same. They're just different ways to measure like how good is the representation. So just look at one is enough, ignore the others, pick your favorite one. Then the three different curves are three different vision transformers of different sizes. The blue one is the smallest one, it's tiny. And the orange one is the largest one, it's L. And so we see here on the x-axis how many images it has seen during pre-training, how many different images, from 100 to 10, in millions, from 100 million to 3 billion, I think. And what we see here is that actually the large model performs much better on the y-axis. Better, lower is better, it's the error rate. So large model performs much better after seeing much fewer images than small model. And it's like almost 2 orders of magnitude here of difference. And this is kind of counterintuitive, or at least it was for us, that a large model is better even after seeing fewer images than a small model. So this, yeah, again, speaks for large models in pre-training. We also found that there are scaling laws that are already well known in language domain for transformers. We also see them in the vision domain, basically. So transformer performance is pretty predictable once we have this good pre-training setup. Okay, so this was all cool, but this is not useful for majority of people because nobody has 3 billion images lying around, right? Nobody can train forever on huge models. So then we asked the question, how would you train your VIT if you don't have these things? And we investigated this quite in depth in another recent paper that is called How to Train Your VIT. And I'm just going to give you the few TLDRs out of that. The first one is kind of obvious in hindsight, at least, and Diet also already hinted in that direction too, is that basically if you add data augmentation and model regularization, augReg just for short, then into your pre-training procedure, then you can get quite a boost. And basically your large data set plus augReg then gives you a model that performs similarly than a 10 times larger data set. And so the largest that I know public image data set that is good for pre-training is ImageNet 21K. And so you add the augReg to this in the right way, and boom, you have a model that is a vision transformer that is similarly good to the JFT 300 million private data set pre-trained one. But the nice thing is this is all public, so we can actually release these checkpoints. And we recently, like just a week or two ago, I don't remember, released these checkpoints. They are now available. But then most people don't want to do this pre-training, but actually have their data set of interest that has maybe like 3,000 or 30,000 images. So we picked a bunch of data sets like this that we took as like representative of what some practitioner might want to do, right? Collect your data set of your very specific application, but then it's not going to be in the millions of images, but in the thousands or 10,000s. And then we wanted to compare from scratch training and the transfer, with transfer being the setting that we proposed from the start. And from scratch, we spent a lot of time on the from scratch training, adding augmentations, regularizations, different training settings, and so on. And we got all of these blue points. Each one is a model trained on that data set. Again, lower is better because y-axis shows error, right? So you can get reasonably good on the medium large data set by spending a lot of time and adding lots of augmentations, regularizations. However, if you just take the model pre-trained on ImageNet 21K, the vision transformer, and just do this very simple transfer recipe that I mentioned before, which is SGD momentum, fine-tuning with the smaller learning rates, and no other special tricks, then you get these dark green points. They are just so much better, especially for the small data set, and you get them in so much less training time that it's, in my mind, it's a no-brainer that if you want to actually do something in practice, you would use pre-trained models and transfer them. There's another question, what if you add augmentation regularization during transfer? These are all the half transparent points here. So you can hit a lot of bad settings, actually. If you're lucky, you can hit even better settings, but in my opinion, not really worth the search. All right, there's a few more insights, but just a small one. If you're interested in small models, here we show that increasing the patch size is actually better to get good small models than making the model smaller. Like here we have tiny model with 16 by 16 patch size is much worse than equally fast base model with 32 by 32 patch size. This is a thing the community seems to have ignored, and everybody has settled on 16, but that's really bad for small models. Right, so all of these are now available by now already in the Vision Transformer repo and the PyTorch Team repo. Hugging Face have Vision Transformers, but not yet the, I believe, not yet the how to train your bit models. But yeah, we released all the models. This was a large study, and there are 50,000 Vision Transformer checkpoints that you could look at, investigate, or not. I had another section on whether we are done with ImageNet or not, but I will skip it in the interest of time, so I can take a few questions. Just check out this paper if you're interested. The answer is like it's complicated, yes and no. All right, but I'm gonna stop here.
Awesome, thank you so much, Luca. Super impressive to see that scale and the results. Amazing. We have actually a lot of questions in the chat. We don't have a lot of time to go through all of them, but maybe we can take one or two at least. Maybe one thing at the very beginning, someone asked if there is like a rule of thumb for parametrization versus dataset size, complexity for vision models.
Yeah, I think so. We didn't really do this here, but I looked a little bit at it. I think you can probably figure out some kind of scaling rules that relate model size, compute that you have available, and the eventual performance and data, assuming infinite data, for example. But we didn't do it all the way here because we ran out of time. And for regularization, actually, I have a slide that I'm skipping here, but in the how to train your bit, we actually try to map out the landscape of like what works for what model size. And there are some surprises, but that I skipped here. For example, augmentation is almost always good, but regularization is not almost always good. And whether it's good or not depends on model size and data set size exactly. You should check out this how to train your bit paper for that one.
Nice, thanks. And maybe one more of the later questions. Let's see. Do you think the inductive bias of assuming sequential data is crucial to the cross-domain success of transformer? For instance, could you still find success in vision if you chose a random way to provide patches?
Yeah, as long as it's consistent, right? Actually, the patches that the vision transformer sees, we don't tell it which ones are neighbors. Actually, here it doesn't really know that this one is to the left of that one and so on. But because we consistently always give them in the same order, then it can eventually over time learn it. And that's kind of what we tried to show here, that the position embeddings actually recover or learn it from the data themselves, what comes from where. So yeah, I don't think that the linearity of the data is an important thing in transformers.
Awesome, thanks so much. I think we'll move to the second talk. I don't know if you have like a few more minutes to stick with us. There's like a bunch more questions. I'll try to make the chat history afterwards available, anonymize it and make it available. If you have time to have a look at one or two more questions, that would be awesome.
Yeah, I can scroll through a few questions now and answer them in the chat also.
Nice, thank you so much. Great talk. Perfect. I think we can maybe move on to the second talk of the day. Ben, if you're ready, feel free to unmute yourself and share your slides.
Yeah, hello.
Perfect. Yeah, the second talk is going to be by Ben Wang while you're setting up your slides, who is an independent AI researcher, and you're contributing to EleutherAI, which is also very exciting, which many of you know is an open source research collective centered around democratizing access to very big AI models, very large scale language models. among others. And yeah, very excited to hear your talk, Ben.
Yeah. So kind of the overall topic of what we'll be talking about today is specifically some of the aspects and kind of challenges with scaling up training to multiple hosts in this new transformer library called Mesh Transformer JAX, which I wrote. So yeah, first, I guess before we start, we can talk a little bit about EleutherAI. So it's a grassroots AI research group that's kind of organizes around a Discord server that's got a heavy focus on scaling as well as democratizing these large AI models. And some notable works that you might have seen before, one includes the Pile, which is a 800 gigabyte dataset of diverse text for language modeling. It's constructed to be similar to OpenAI's data for GPT-3, but more diverse. So it includes a lot of data sets, including GitHub, PubMed, Common Crawl, Arxiv, etc. And kind of interesting is that the inclusion of GitHub means that all of these models that have been released by EleutherAI are actually quite good at writing code, which is pretty cool given GitHub Copilot and things like that. Shows that is quite a interesting use case. And another work that's been released is GPT Neo, which is a mesh TensorFlow based transformer implementation. And that has 1.3 billion and 2.7 billion models released. And kind of the topic of this talk is Mesh Transformer JAX, which is a JAX-based model parallel transformer implementation. And this has a 6 billion parameter model released, which is trained on the Pile as well. And the model is called GPT J6B. And to talk a little bit more about the model, it's a 6.1 billion parameter autoregressive language model. It's also trained on the Pile, like all the other ones. And it has comparable performance to the GPT-3 6.7 billion version. It's trained with Mesh Transformer JAX. It has fully open source code and weights under the Apache 2.0 license. And it performs 8-way Megatron LM style model parallelism. I'll talk a little bit more about that later. And it's trained on a TPU v3 256 for about 4 weeks. And there is Hugging Face / PyTorch support in a pull request, but it hasn't been merged yet. Hopefully that'll go through soon. So I guess you can use it through Hugging Face. And kind of the meat of the talk would be, so first we'll talk about kind of the JAX programming model across multiple hosts as well as multiple devices, which is a SPMD model, which stands for single program multiple data. And then we'll talk a bit about the design philosophy of kind of this code base as well as the overall architecture. Then we'll talk about kind of the design challenges specific to training across multiple hosts, including code distribution and data loading. And then we'll talk about some future directions, which include swarm training. So the JAX SPMD programming model on a single TPU basically means that when you parallelize code to run between the cores, all the cores must run the exact same code. When I say parallelizing code, that means a lot of different operators, which include PMAP, XMAP, PJIT. Like all of these operators, they rely on this assumption essentially. So we can do a simple example of a PMAP computation. So we create an input, which is just numbers 0 to 3, and then we run a PMAP computation, which would square each number. And to see how this would actually get executed, so this is a hypothetical 4-core TPU. It doesn't exist as far as I know, but it'll be too difficult to draw more cores than this. So in the first line that runs, the input equals jmp.arrange4, that actually creates variables that just lie on the first TPU core, essentially. So you have the 4 numbers and they all lie on the first TPU core. And then when you get into the PMAP computation, the first thing that happens in the computation is that it would actually shard the inputs. So it would place each part of the array on a separate core. And then you have your PMAP computation that runs, which runs across all the cores. It must be the same. And then the outputs you get returned. And that gets returned. It kind of looks like a single array, but it's actually a class called sharded device array, which means that kind of each element of the array actually lies on a different core. So you can kind of interact with it as if it was a single array, but like it actually, but like the backing store for that array is sharded. So I mean, this seems relatively straightforward on a single TPU, but when you try to scale up to multiple TPUs on a TPU pod, it gets a little bit more complicated. So a TPU pod, it looks very similar to just multiple TPUs. Here we have two 4-core TPU hosts, and they are exactly the same, but the only difference is that they have a different host index. So the first host has host index 0, the second host has host index 1. And the assumption still needs to hold that when you parallelize code between the nodes, all the cores must still run the same code. So I guess we can try to do another PMAP computation similar to the first one. So here we have the same line of code from before, JMP range 4, but that kind of doesn't do the right thing because it will have the array of 0 to 3 on the first host, as well as 0 to 3 on the second host. So what you need to do is you actually need to do something based on the host index. So in this case, we would add host index times 4, which would mean that the first host has the numbers 0 to 3 on it, the second host has the numbers 4 to 7. And then you have this kind of virtual array that is 0 to 7. And then you do the same PMAP computation. And this Python code must be run on all the TPU hosts on the pod. And if you do that, kind of this is what it looks like. So you have the same unsharded inputs as before, except so kind of each host looks at like one part. So it looks like it looks at one part of the inputs that gets distributed to the local TPU cores. And then the similar process for sharding the inputs happens, but when the inputs get sharded, it actually happens across the whole TPU pod. And then so does the PMAP computation. So yeah, and when the outputs get returned, we have something similar, but kind of each TPU, like on each TPU host, you only see a part of the output. You only see the part of the output that corresponds to the cores on the TPU host. So the first host sees sees the first 4 elements. The second host sees the second 4 elements. Yeah, so kind of this is basically how you can scale above just 8 TPU cores. You can go to a lot more. Yeah, so now we'll move a little bit into talking about how Mesh Transformer JAX is designed. So kind of the most important design philosophy is I did not want to spend too much time running it. So it was to minimize the developer hours for writing the framework and for kind of producing this artifact of a large model. So this code base is quite simple. The total code for model training is only about 1,000 lines of code, which compared to things like Megatron is like about an order of magnitude less. And there's some other stuff like model evaluation, model inferencing, and things like that, which make about the total code about 2,000 lines of code. And kind of because this is only going to train a few models, verbosity works over abstraction. So there's very few like options for these different models, and there's quite a few hyperparameters. For a lot of them, I just picked a sensible default and just ran it at that. So it's mostly simple straight line code. There's nothing crazy going on. So yeah, it's only designed to train a few models, might make it so complicated. And another one that kind of stems from the other two is that simplicity often is better over scalability. So it has a very simple parallelism scheme, which is similar to the original Megatron LM. And what that does essentially is the hidden dimension gets replicated across all the devices, but kind of the feedforward dimension and the heads are sharded across the devices. So that kind of minimizes the amount of monoparallel communication you need. compared to some other approaches. And there's kind of no really exotic optimizations. It's just very simple monoparallel and data parallel computation. So there's no such thing like we don't do zero or pipeline parallelism or anything crazy. So kind of given this philosophy, this is the architecture that we came up with. So first you have a bunch of TPU hosts. So like when you create a TPU pod, this is what you get. You get for, or in this case, but up to like 32 or even more TPU hosts. And between the TPU hosts, there is a high-speed networking. There's a high-speed network that connects all the TPUs. And that's where all the kind of the monoparallel, data parallel communication happens. And then we also have a separate driver virtual machine, which is a Google Cloud Cloud VM that's on the same region in the same zone as these TPU hosts, and it kind of does coordination. So it kind of talks to all the TPU hosts. It uses RPC calls, so it essentially can call remote functions on the TPU hosts, and this essentially allows everything to happen on the same order on all the TPU hosts. So the driver VM makes sure that if it runs a training step on one host, it runs it on every other host. So that kind of maintains the invariant that all the hosts and all the cores run all the same code. And the library that was used for these RPC calls was Ray. Seems to work quite well. Pretty fast, low overhead, and it scales at least up to the pod sizes that I've been doing. Yeah, so this seems somewhat straightforward, but there are some challenges kind of unique to this multi-host training system. So the first is that every code must run the same computation. RPC helps a little bit with that by making sure everything runs in the same order, but kind of how does the actual code get to the virtual machines, get to the TPU host? And then you also have the challenge that every node needs to see different data. So how does this data get distributed? So the first thing would be the code distribution. So it's kind of problematic. You have to install dependencies. You must have the same versions, and you also must just copy the code to all the nodes. So a obvious question is where do you actually copy it from? Do you do it from like GitHub or like your local machine? Like where does it come from? And you also must be able to scale it to many nodes. So the V3-256 has 32 host nodes. That's quite a few, but not that many. But if you wanted to scale to something bigger, like a 2048, that has hundreds of host nodes. So if it's slow, your training will take a long time to start. So what I ended up going with was kind of looking at this problem as kind of like a server orchestration problem, and there are existing tools for doing that. For example, shell scripts, Kubernetes, Docker, etc. And kind of there's a general trend with these tools that as you get more robust, you also get less simple, you get more complex. So I decided to go with simplicity over robustness because like if there's only one training run going on, it's not like if it breaks, I can fix it. And there's kind of the uptime of the training isn't the most important. So we have shell scripts that install dependencies and SCP that copies code from the local directory to other VMs. So yeah, pretty simple setup. And with data loading, there are some other challenges with this as well. So first is shuffling. So when you're training these large models, it's very important to make sure that the data is shuffled at both a document level as well as the context window level. So kind of when if you only shuffle at the document level, then, and if you have like really long documents, that could mean your kind of batch is just made out of one document. which is really, really bad for convergence as well as for stability. So it's very important to make sure shuffling is done well. Another thing is that resume must be implemented efficiently. I was training on preemptible TPU pods. So that means, every few hours, the TPU pod would preempt, and I'll have to restart the training from a checkpoint. So it's important that resume is efficient and fast, because if it's slow, then a lot of your time will actually be spent resuming from a checkpoint rather than training. So with some solutions like TF data, it's actually hard to resume without reading like a significant fraction of all the data that you've trained on previously. It might not be a big issue with things like images, where with image data sets where you do like a lot of epochs, but here you only do one epoch, so you have to read terabytes of stuff to kind of get to the same spot. And then you also have the coordination challenge of how you make sure that no two hosts train on the same data, because if they do, then you're kind of wasting a lot of your compute. So what we decided to go with is, so first we have this like very similar architecture from before, driver VM to the TPU hosts, RPC done with RAID. So the first decision that was made was actually to read the data, to do the data loading on the driver VM and to distribute it to all the hosts. So that means there's only kind of a single, process that is doing the data loading. And it reads TF record files from Google Cloud Storage buckets. So shuffling is done kind of before all this. So it's not even kind of in this code base. So it's important to do like a per document and per sequence pre-shuffle. And because you're only doing one epoch, it makes it quite easy. You don't really have to worry about kind of reshuffling between epochs. You can just kind of go through the TF records one by one. So there's an index file which contains each TF record, and then it kind of just perfectly sequentially goes through all these TF records. So it goes through the list of TF records, and within each TF record, it goes through each example sequentially. So what that means is, as long as you save which TF record you were reading and how far you were through it, you only need to kind of read through one TF record. So that's only a very small fraction of your total training data. And kind of the driver VM also makes sure that it distributes data evenly. It doesn't send the same data to multiple TPU hosts. And this seems to work quite well. I think overall, the data loading challenges are not too significant for at least these text models. I don't think this architecture would work very well for vision models, for example. It works well for text models because the input and output data rates are so low, on the order of hundreds of kilobits per second, that you don't really need to worry about making this too efficient. So something simple just works well. Yeah, and I guess next I can talk about some possible future directions. So kind of all the stuff that's been talked about for now has been you're training on a single big TPU pod. However, smaller TPU pods, it's usually easier to get capacity on. So the question is, how do you combine multiple TPU pods into one training run? So you have some other possible complexities. You can have heterogeneous pods, so you can have a mix of V2, V3 TPUs, and these pods would also be preemptible. So any node can go down at any time. So this is kind of quite a difficult challenge. So one way of approaching this is fault-tolerant data parallelism. There's this paper that was actually by some people from Hugging Face, which essentially does data parallelism and just does a kind of fault tolerant or reduce of the gradients at the end of each step. But here, kind of the problem is that the model size that you can use is limited by the size of the smallest device. That might not matter too much for if you're doing small models, but for kind of these like really big, multi-billion parameter models, it does make it is quite a challenge. So kind of the smallest device that that the GPT-J6B training would fit on is a 8-core V3 pod, and it would not fit on a 8-core V2 pod. So you would need kind of so like the unit of pod you get must be pretty big, especially as you're considering even larger models. And then another approach is pipeline parallelism. So that's kind of, I've been working on that in a separate repository called Swarm JAX, and also Cohere. They might talk about this. It's yeah, they'll be talking. They'll be the last talk of the day, I think. So yeah, I think kind of these. So both these approaches are pretty promising. And I think something like that would be necessary for efficiently training large models in the future. So yeah, that's all I have. Thanks for listening. Happy to answer some questions.
Very cool. Thank you so much. Great work. Interesting architecture, and also to see like the design philosophy and the design choices you made. Pretty cool. We have a few questions. Maybe let me start with the first one on top. What exactly is a one epoch? What exactly is one epoch regime?
Right. Yeah. So one epoch basically means you just go through all the data once, rather than kind of training multiple times on the data. So that's kind of I guess one epoch regime is pretty specific to just large language models. I don't know anyone else does that, because kind of with language models, it's quite easy to get large amounts of text, and each token is quite and each token is quite expensive computation wise. So it's easy enough to get enough data such that you only have the compute to do one epoch.
We have two related, more general questions. How many people work concurrently on the project and implementations, and what does mesh and mesh transformer refer to?
Yeah. So the code on this was written entirely by me, and another contributor, Aaron. He kind of helped with hyperparameter selection and some debugging. The mesh in mesh transformer kind of is, I think it comes from mesh TensorFlow, I guess, and that comes from the kind of how like the way that that these arrays are distributed across the TPU. So yeah, kind of it's like a yeah. So I think it's something like that, I guess.
Cool. And maybe the last question is, I can see now, is the data loading pipeline fully reproducible given preemptions? If not, have you thought about whether it could be done efficiently? Yeah,
so the data loading is fully reproducible. There's basically you save like how many batches you are through each TF records and which TF record you are at, and that allows you to perfectly reproducibly do this. I think most of the reproducibility challenges comes from the shuffling step, and because here we don't actually do any shuffling in this repository, it makes it quite easy.
I think that's the, yeah, Very cool. That was the last question. So thank you so much again, Ben. Super interesting work. And yeah, I think we can maybe move on to the third talk of today. I think our speakers should be all here by now. Let me just double check.
Yes, I'm here. Can you hear me?
Perfect. I think Soňa is also here. And let me just make Junhyuk unmute.
Okay, I've just shared my screen. Can you see it?
Yes, looks good. I'm just checking in with Junhyuk if everything works on his side. Junhyuk, you should be able to unmute yourself, I think, or?
Yeah, I think I'm unmuted. I can speak now.
Perfect. Yeah. Soňa should be also ready, right? Yeah. Perfect. Okay. Nice. So I think we can start with the third talk. I'm very excited to welcome Iurii, Kemaev, Soňa, Mokrá, and Junhyuk all from DeepMind, and to hear about the DeepMind JAX ecosystem.
Yeah, thanks for the introduction. So my name is Iurii, and together with Soňa and Junhyuk, we're going to tell you about how we use JAX at DeepMind. And starting with our DeepMind JAX ecosystem, which is essentially a collection of JAX libraries that we have been developing over the last 2 years. So why an ecosystem? Well, DeepMind researchers have had great initial success with JAX in its early days. And the question that naturally arose is, how can we continue to support and accelerate this great initial work? And there are a few considerations that we took into account when kind of making a decision about creating an ecosystem. The first of which is that JAX is not a vertically integrated machine learning framework, but rather a set of very powerful and flexible function transformations, for example, GRAD and PMAP, which gives us a huge freedom, a great freedom to implement a variety of tools on top of it to basically support our rapidly evolving requirements. Besides, we really want new tools to be consistent and compatible with the previously released frameworks like Sonnet and Truffle from the TensorFlow land. So to accomplish this and other goals, we decided to develop an ecosystem of libraries of reusable, independent, and unopinionated JAX components. And under reusable here, I mean that this should be flexible at first. They should be up to date and have a low entry threshold. Independent means that they can nicely integrate with each other, but more importantly, can be used seamlessly in separation. And unopinionated means that they are not biased towards any concrete approach or paradigm to basically be able to quickly implement new ideas and basically contribute them back into community. And each library is intended to do one thing really well, and it supports incremental buy-in. And we'll see some examples in the next slide. Last but certainly not least, we are open sourcing everything to basically enable research idea sharing and to ensure that the results obtained using this library and this ecosystem are reproducible outside of DeepMind. So in the next few slides, I will show you 3 examples of the libraries that are part of the ecosystem. And we're starting with Haiku. Haiku is the library for neural networks, and the motivation behind it boils down to the fact that much of the power of JAX comes from the functional programming paradigm, whereby we have functions that are stateless or pure, and we have different function transformations that produce another pure stateless function that can be applied to any kind of numerical data like tensors. However, like the common abstractions in the machine learning area, for example, trainable neural network parameters or neural network state, think of patch norm state, fit potentially a bit better to the object-oriented paradigm, or at least this is how people are used to think about it. So Haiku kind of bridges the gap between these two worlds, between the world of object-oriented programming and the world of functional programming, by providing a set of tools to convert stateful functors, such as neural networks, into init and apply pure functions, stateless functions. Hence, they can be used directly in JAX. And our researchers had a great success with trivially porting the previous results from TensorFlow, such as AlphaStar and AlphaFold, into the JAX world. Yes, so this library is stable, mature, and it's widely adopted within DeepMind and Google and the public community as well as the other examples. So the next example is Optics. Optics is for optimization, and optimizers are also stateful mostly, and as Haiku bridges the gap between object-oriented paradigm and the functional paradigm for neural networks, Optics effectively does it for optimizers. And one crucial observation here is that basically things like Atom, Momentum, and I know SGD can be implemented as a chain operator of simple gradient processing primitives. And these are the first things that Optics implements. And then using these primitives, it kind of provides a zoo of the common optimizers that people know, use, and love. And of course, obviously, users are free to use these primitives to implement their own optimizers, their own optimization algorithms, and try out new ideas. So Optics nicely integrates into place with Haiku, but more importantly, its scope is much wider, and it can be seamlessly integrated into common JAX neural network libraries such as Flax, and potentially in anything that represents parameters as a tree of tensors. So the last example for today is RealX, and as you may know, DeepMind cares quite a lot about reinforcement learning. And one well-known complexity of it is that it's quite easy to get things wrong. For example, if you place stop gradient in the wrong place, that can completely jeopardize your whole research effort, in a sense that you will still be observing somewhat meaningful and probably even interesting, yet completely delusive results. And it can take some time, it can take some significant amount of time to detect this kind of errors. And the idea behind RealX is to provide a collection of trusted and battle-tested components for building reinforcement learning algorithms that are common for them. And for example, on the right-hand side, you can see how two of such primitives, that is Q-learning and Cohere's laws, can be combined to define loss functions that you might want to use in your Q-learning algorithm. And in case of RealX, a lot of emphasis was put on readability. So if you look at the doc strings of RealX, you will find actual excerpts from the textbooks with conventional reinforcement learning notation, and these are intended to be self-explanatory, basically. Okay, so I'm afraid I don't have enough time to cover all the libraries that constitute the JAX ecosystem today, but there are definitely more. For example, we have Giraffe, which is a library for graph neural networks processing, JAX for debugging, testing, reliability, and we have Distrax for mastering probability distributions, which is fully compatible with TensorFlow probability, for example, and in fact they are interoperable in the JAX land. Plus we have few more that are on our roadmap and we will probably release soon. it's worth mentioning that there's another separate layer of frameworks built on top of the JAX ecosystem, both within the DeepMind, such as JAX and Acme, and outside the DeepMind, such as Flax, JAX-MD, and JAX-Chem. So I highly encourage you to check them out for more details. Also, there is a blog post about with a nice overview of the existing libraries we have at deepmind.com. And yeah, that's it from me. With this, I think the rest of this part of the talk, Junhyuk and Soňa will tell you about their research, which is based on JAX and JAX ecosystem. And basically, yeah, with this, over to you, Soňa.
Hello. I hope that you can hear me and see me. Oh, great. Yeah, so yeah, hello, everyone. My name is Soňa, and I will talk a bit about what makes JAX great for generative models, specifically for GANs. Next slide, please. Okay, so generative adversarial networks, or GANs, are a bit different to many other more standard generative models, as they don't follow the paradigm of one model, one loss. In GANs, we have two players. There is the generator, which produces the data, and there is a discriminator, which has to distinguish the real data from the generated data. And these two players compete with each other. So the discriminator really wants to be as good as possible in knowing when data is real and when it's fake. And the generator tries to fool the discriminator into thinking its creations are from the real data set. There are multiple ways to implement this, which we are not going to discuss, but the key point is that we have two players playing against each other, hence the name adversarial. Next slide, please. Okay, so one thing that we might want to do when implementing a GAN is to have multiple discriminator updates per single generator update, or maybe the other way around, but I think this is usually done. This is really easy in JAX because you just write a single for loop for the discriminator update and a separate for loop for the generator update, and choose however many iterations you want in each of them. Let's look at the example of the discriminator update in the slide. So that's the first block. You can see that we've wrapped the discriminator loss with the JAX grad method and then evaluate it at the current values of the discriminator and generator parameters. So the grad method returns us the full gradient function, so not just the values, but the actual function. And this is a gradient with respect to the first argument. So in this case, this would be the discriminator parameters. So notice that there is no need to stop the gradient to the generator parameters or anything like that, because the gradient functions works like this, like it will differentiate with respect to the first parameter, the first argument. We know that that's just the discriminator parameters, and it doesn't matter that we then evaluate it using generator parameters. Yeah, looking at it, the next step that you do is that you explicitly pass the gradients to your optimizer's update function, and then you apply the updates to get the new parameters. And then for the generator, you do exactly the same thing. So, but this time you use the generator loss, and you can see that this generator loss takes the generator parameters as the first argument. So we know that the gradient will be taken with respect to the generator parameters this time. And that means that you are going to update the generator this time only. Notice that the code looks very similar to what a pseudocode would look like for GAN, right? Like it's a get a gradient, evaluate it, update, like apply the updates. So I think this is quite neat, that basically it makes the code very clean and easy to read and understand. Next slide, please. Thank you. So one more thing to highlight about this is that we have direct access to the gradients, so they are not just hidden somewhere. If we want to somehow track them, for example, we might want to see what the norm of the gradient looks like at different layers. we can do this very easily because the values are available to us. We can just add a couple of lines of NumPy that we are all like mostly familiar with, and then just log the statistics in a way that we find useful. And yeah, this is very important because tracking statistics like this helps a lot in building intuitions about what our models are actually doing. So yeah, I think it's really nice and cool that you can do it very easily without much additional work in JAX. Next slide, please. So another thing that is quite natural in JAX is that JAX gives you direct control and makes you think about some decisions that you have to make instead of just making these decisions under the hood without you even realizing that something's happening. So for example, let's talk about this. Like when you're updating the discriminator, what should you do about the state of a generator? And by state, I don't mean the parameters this time. I mean more something like, for example, batch norm statistics for the generator. So yeah, do we want to update this too? Yeah, let's not talk about what we actually want to do in GANs. The key point is that it's a thing you might want to think about and decide consciously about instead of letting the framework do the work. In this slide, you can see that we are sampling from the generator. We are passing in this state.gen variable, which is the original state value of the state in generator. And this function is returning us a new value for this, which we are saving in a gen state variable. And then at the end of this method, we are returning the two states, the discriminator and generator state, and we decided to return the new value of the state. Alternatively, if we decide that we actually don't want to update the generator state, next slide, please. Yeah, so this is very easy. You just don't use it, meaning when you are calling the sample method, you use the state.gen to pass it there, and you just ignore whatever is returned. And when it comes to returning from this method, you just return the original value of the state.gen. So this way, you know that the generator state is not going to get updated just because you know that you ignored the value for the update. So it will not be used. Okay, now next slide, please. Yeah, so this is the last thing I would like to point out, which in relation to GANs. So we often use this reparametrization trick in GANs, which is a thing that sometimes we need to differentiate with respect to parameters of a distribution that we sample from. So you can see that there is this expected value, and usually we would estimate this expectation, for example, by sampling multiple times from this distribution. And this is a problem. It's quite difficult to differentiate random like things that are random. So instead, if we can, we will try to change the parameters in a way that the randomness gets extracted out to a separate variable, and which is no longer dependent on the parameters. So this might be a bit confusing, but I don't know, think about instead of sampling from a normal distribution with some mean and variance, we will sample from a standard normal, and then we will just multiply by sigma and add the mean. So now the sigma and mean are sort of separate from the part where we are sampling. And yet, what is the example here is showing how to calculate the Jacobian in such a case of a reparameterized function. And what is nice about doing this in JAX is that we can vectorize our function very easily. So the function f, maybe if it's a neural network, maybe it's very trivial to vectorize it, but it doesn't have to be a neural network. It might be something more complicated. And yeah, we don't have to rewrite it at all. We can just use this jax.vmap and wrap it around our function, and that automatically handles taking and returning vector inputs. And yeah, as a bonus, you can see that there is actually a built-in Jacobian function in JAX, which you can then apply on top of this, which will automatically give you the Jacobian, so gradient functions for each element in the batch. This usually makes the testing much cleaner as well. For example, because you don't have to worry about this like vectorization, like broadcasting manually, since it will all be taken care of by the VMAP. Yeah, so I think that's all from me. So thank you very much for your attention. And I think Jun will now talk about metagradients.
Yeah, thanks. So hi, everyone. I'm Jun. I'm going to briefly talk about how we use JAX for our recent work on discovering reinforcement learning algorithms. So if you go to the next slide. So in this project, we wanted to meta-learn an entire reinforcement learning update rule from a distribution of agents and distribution of environments. But there were several technical challenges in this project. So if you go next. So first of all, we wanted to simulate many independent learning agents where each agent is interacting with its own set of environments. So this is already quite unusual because normally in reinforcement learning, we consider just one learning agent, but we wanted to simulate many different agents in this framework. But at the same time, we wanted to apply the same update rule, which is the meta learner in this case, across 4 different learning agents in a synchronized way. And also, we wanted to calculate the meta gradient over the update procedure, which requires calculating the second order gradient. And finally, we also wanted to massively scale up this approach by increasing the number of learning agents without introducing any extra cost. So to tackle all these challenges, we first implemented all the environments in JAX, and we first implemented a single update rule, single agent, and single JAX environment interaction, as you can see from this figure. And then in the next slide, we added a VMAP over the environments to implement multiple environments interacting with a single agent. And if you go to the next slide, we then added another VMAP at the outer scope to simulate multiple independent learning agents, and each agent still has their own set of environments. And finally, if you go to the next slide, we added a PMAP over the entire computation graph to implement the same computation graph across many different TPU cores and distribute this computation graph across many different TPU cores. And still, all of these TPU cores have a single shared global update rule, but they all simulate their own set of agents and own set of environments. So if you go to the next slide, this is the pseudocode of our framework. So the top part implements the agent update, and the bottom part implements the meta gradient calculation. And these VMAPs and PMAPs, the yellow parts are essentially the VMAPs and PMAPs that I just described in the previous slides. So without these VMAPs and PMAPs, this pseudocode essentially implements a single agent, single update rule, single environment interaction. But by just adding a few VMAPs and PMAPs, we were actually able to massively scale up the approach. So in the actual experiment, we used 16-core TPU, and using this, we were able to simulate 1,000 parallel learning agents and 60,000 parallel environments with a single global shared update rule. And also, we were able to process more than 3 million steps per second, which was amazing for us. So if you go to the next slide. Yeah, to just summarize, we basically had several challenges, including simulating multiple agents and calculating meta gradient and so on. But by using JAX, we were actually able to handle all these challenges quite easily without putting much engineering effort. And also, out of this project, we also meta-learned quite interesting reinforcement learning update rule out of many agents and many environments. And you can maybe check out the paper if you are interested. So yeah, that's all we have for today. So if you have any questions, we will take the questions now.
Thank you so much. Super interesting. We had a lot of conversations and comments and feedback in the chat. I'll read a bit out to you. First of all, just someone said, wow, I think this use case really highlights the abstraction of VMAP and PMAP, and super interesting to see how by using it, you can scale up to 1,000 agents. So super impressive. There was also lots of love for the ecosystem and the libraries. So a lot of good feedback on that. We have a question if the code is shared, if it's open.
If you are asking about the final project that I just described, unfortunately, the code is not public yet, so it actually requires a bit of open sourcing process to be able to share. But yeah, I think there is like a public implementation by someone else, so maybe you can check out that.
Is it planned to do open source or not yet?
For now, we don't have a specific plan for that. So, but I guess we are basically continuing this effort. So at some point, we might be able to open source our implementation.
And there was one question, maybe going back to the more kind of initial part of the talk. Someone asked if, after like loving the ecosystem and the libraries and looking at this, if there are any plans for an API or a kind of conceptual harmonization between Haiku and Flax?
That's a great question. I don't really know, but the fact is that these two libraries were developed independently in the early days of JAX. So I think they should be interoperable in some sense, but I haven't checked it, so I can't tell for sure, say for sure. Yes, Optics works with Flax, that's true. Optics works with everything that represents parameters as trees of tensors. That JAX also allows for an interoperability with MLIR. I don't know. Can say. Need to check this.
Do we have any other questions for the speakers? Yeah, it was mostly a lot of like, I don't know if you had time like to have a quick look at the chat, but a lot of like funny and great feedback and back and forth. Yeah, maybe last comment, if the slides will be shared or the links in the papers.
I need to check in with the best person of contact from DeepMind for this.
No problem, but I can definitely share some. Yeah, sounds great. I'll definitely share maybe some of the papers as links maybe later on in the chat and on Slack. And yeah, definitely check out the libraries. Perfect. Then yeah, somebody said when the videos are up, the slides will be there. So yeah, the great kind of news is definitely that we will be able to, or hopefully we'll be able to see the video later on. But yeah, we're checking in for that as well. So please stay tuned. If we don't have any more questions, thank you so much for the talk. This was really super great to see how the JAX ecosystem is a DeepMind and how you're using it. So thank you so much, really appreciate it. And I think it's time to move on to the fourth talk. I hope all of our speakers are there. I think I've seen them, can unmute themselves. And if you're ready, you can share your slides. We have Sid, João, and Joanna from Cohere today, and they will talk about large language modeling.
Yeah, I think we are all here. Now we'll start sharing.
Perfect.
Yeah, Joanna, can you see the screen?
Yes. Sorry, I'm trying to. Okay, perfect. Hey, everyone, thank you for coming today. We are very excited to share what we are doing in Cohere. And so today, Sid, João, and I are going to talk about Cohere's journey on building a large-scale language model and how the recent development of TPU-VM and JAX led us to the improvement in our model parallelism framework. So before we start, let me introduce Cohere to you. We're an early stage startup based in Toronto that builds large-scale language models. We're fairly new, just around 2 years old, but we are rapidly growing with 30 people in our team. And the first three over here are our co-founders, Aiden, Nick, and Ivan. So Aiden and Nick are from Google Brain, and Ivan was working on large-scale language model like serving around 2 years ago. And our mission is to build machines that understand the world and to make them safely accessible to all. So specifically, we are focusing on building safe, highly scalable, and highly performant language models that could easily be accessed by our API endpoints. So what that means for us, for scalability, the modeling team has been working on creating a model framework called Megazord. So Megazord is a model parallelism framework that distributes the model across multiple devices. And the core idea behind this is the pipeline parallelism, specifically gpipe. So for those of you who aren't too familiar with the pipeline parallelism, so gpipe is a model parallelism technique in multi-device setup where we break down a batch into multiple microbatches and send those microbatches to the next device. So the device after doesn't need to wait for the whole batch to be done. So for this diagram, each row in the diagram, like on top and bottom, are the individual devices that can be run in parallel. And the squares here are the scheduled job for each microbatch. The diagram on the top describes a naive model parallelism, and the bottom one describes gpipe. So for the naive model parallelism, so imagine you have a batch size of 32. So the F0 here will try to finish the whole job of the 32 batch size, and the rest of the device will be idle waiting for the first device to be done. And just only when the 32 batch size is done from the first device, it'll move on to the second, and the bottleneck is still there all the way until the top. So for gpipe, what happens is, so say you break it down to 4 microbatches. So the first device will work on the batch size of 8 first, and then we'll pass this down to the second device. And while the second device is working on the first part of the batch, the first device is also working on the first batch, which is the second part of the first batch. So while doing that, it reduces the bubble in the middle. Like the bubble actually means like the idle time of the device. And yeah, so if you imagine the F0 on the top being as long as the F00 and F03 combined, you will see a considerable amount of bubble in the naive model parallelism, but gpipe actually reduces it, and this results in the sublinear step time increase when you're increasing the model linearly. So I'll get the questions from the end, but yeah, going back to the Megazord, we placed each TPU on separate processes and piped the activations in gradients. So as an early stage startup, we mainly use TPU v38s, often preemptible ones, because we wanted to scale up the model while being cost aware. And for the context, we did not have a TPU VM as our option last year. So our initial stack included regular TPU nodes, TensorFlow 2, and Python multiprocessing library. So for us, not having TPU VM was a very big deal because it meant that we did not have direct access to communication between TPUs, and all the tensor communication had to pass through our host machine. So a forward pass looks something like this. So the first TPU would process the first micro batch. It'll send it to the host machine, and the host machine will acknowledge the activation, and it'll send it to the second TPU for the next propagation. And the backward pass looks very similar. It just flows the other way around. The last TPU will get the loss and gradients from the last TPU. It gets sent back to the host machine, and the host machine will send it to the second last. And yes, we personify TPU and Cohere. So for us, this is what we call Megazord version 1. And Megazord V1 allowed us to scale up our model size and build a product around this. But it has some major drawbacks that you saw earlier. So the biggest one was this double communication, which drastically increased the communication. So we were spending way too much time on communication, and this bottleneck limited us from effectively scaling up. Also, there were a lot of manual tensor handling since a multiprocessing library was very low level for us, and pretty much everything needed to be handled by queues. So now I'm going to pass this to Sid so that he can talk about the version 2.
Yeah, thanks for that, Joanna. And so Megazord V2, we really wanted to cut down on the communication cost we had to pay in V1 because, like Joanna mentioned, it was really preventing us from scaling up or getting to the scale that we wanted to get to. So with the advent of TPU VMs and by using Ray, that really improved the spend time in communication, and we spent less time for each step compared to Megazord V1. Because what TPU VMs enabled for us was TPU to TPU communication, like directly transferring activations and gradients between TPUs. Because TPU, I can just spin up a Ray cluster and make my host machine the head node, and the TPU VMs are the child nodes, and they just communicate with each other without having to go through the host machine all the time. And this communication cost reduction was really helpful in scaling up. And the queue handling became a lot more simplified because we did not need to explicitly handle all these transfers, all the pre-processing, post-processing associated with transfers from TPU device to TPU node to host machine. And now with TPU VMs and Ray, that became much more simpler. One thing to note is that we were still using Megazord V2 with gpipe. So which means that if you go back, there's still this bubble where your TPU cores have an idle time. They're doing nothing in this bubble stage. So with pipeline parallelism, we were getting the scale that we wanted to, but the code utilization is one aspect that we wanted to improve upon. And the training looked something like this in Megazord V2, where the host machine sends the input to the let's say you have 16 layers and 4 devices. You can split up these 16 layers into 4 chunks of 4 layers each and place them on each device. TPU1 has the first 4, TPU2 has the second 4, and so on. So the input gets sent to TPU1, and the output from the first 4 layers and the activations go to TPU2, and they just directly talk to each other. And TPU4 evaluates the loss and just sends it back, computes the gradients, and you just keep computing the gradients until TPU1 and send it back to host machine for metrics or for whatever checkpointing and whatever you want to do after each train step. So we basically halved the communication time because there was no longer the host interference in each and every tensor transfer stage. So with this in mind, given the context of Megazord V1 and Megazord V2, we already started thinking about the next generation of Megazord and what we needed in the next generation of Megazord. And one thing was mesh level parallelism that we were really excited about. If you were here for Ben's talk earlier, he mentioned his mesh transformer work also uses mesh level parallelism. And this is appealing to us because even though in Megazord V2 we had RAI and TPU VMs, these are individual different machines like TPU VMs, and the communication was still, it wasn't negligible cost. And with TPU pod slices, you have multiple TPU VMs that are actually connected to each other in a grid-like structure. So, which means that your communication time is much, much lesser because they're actually physically connected. And we wanted to take advantage of this mesh level parallelism. And if you weren't there for the talk, one sentence description could be, if you have a grid of devices and you have two axes, X and Y, could be a Z axis as well. But for now, if you have X and Y axis, and on the X axis, you can have model level parallelism, and on the Y axis, you can have data level parallelism. So what this ensures is that all of your cores in this grid of TPU devices are being utilized all the time. So there's very minimal, there's little to no idle time in this mesh level parallelism. And one thing was, since Megazord V1 and V2 were using TensorFlow 2.0, and the only thing that we were familiar with was Mesh TensorFlow, which provided this mesh abstractions so that we can implement this. But the issue was Mesh TensorFlow primarily worked with TensorFlow 1 and not 2.0, and integrating it into a code base that we were already working on was very challenging. And so we ruled out Mesh TensorFlow as an option, and we started looking towards other things. And in the next generation, we also wanted to alleviate communication costs by taking advantage of mesh level parallelism and TPU pod slices and long-term scalability. So by our learnings from V1 and V2, and when we implement V3, what we have in mind is making this framework relatively future-proof. So we do not want to keep suffering these communication costs and all of the latency issues that come with V1 and V2. So keeping that in mind was really important to us, so that we can get to scale as much as we need without being bottlenecked by any kind of communication issues or infrastructure issues. And another super important thing for us was the barrier to entry should be super low. And what I mean by that is, at Cohere, we have Megazord team, which focuses on scaling up, and the modeling team, which focuses on trying new experiments and ideas and stuff. So we want the barrier between these two teams to be as low as possible. If someone from modeling team wants to get into scaling up and contribute some code to it or some new functionality to it, we really wanted to make it as easy as possible. But with V1 and V2, that was not the case, because you have the TensorFlow has kind of a complicated, at least our experience has been, but it's kind of obfuscated abstractions with TPU cluster resolver and TPU basically it's not easy to work with, and it's not very straightforward. So we wanted to, when deciding about the next generation, we wanted to choose a framework that makes things as simple and as intuitive as possible. And with JAX, it's cheesy, but it was love at first sight because it gives us a sense of familiarity. JAX is very much like NumPy, but with autodiff. And when we're writing out a new framework, that sense of familiarity can really accelerate the development process, and which was really important to us. And I'll leave it to João to talk more about JAX and Flax and what we're doing with that at Cohere. And yeah.
Okay, so yeah, JAX for Flax, and why is it good? First of all, it's very easy to convert your code to JAX, and in fact, it's just that it's easy in general to code in JAX. You can get a lot done with very few lines of code, and so the whole migration process that's generally pretty painful is being sweet and nice in general. So yeah, easy to work with. We have VMAP that makes a lot of code much simpler. We have the compositional transformations, which is just a better way to code in general, a better way to model your stuff. We have grad, VJP, and JVP, which are like vector Jacobian product and the opposite. So now we can get gradients with respect to different function arguments in a very intuitive and very simple way. And that's again useful when you're trying to do this pipeline parallelism, and it's also useful to write more complex optimization methods. So second-degree optimization, like shampoo that João and you talked about yesterday. Adversarial optimization, it's an area that's growing and that's showing like amazing results, like the Berta. Also, more and more papers are being implemented in JAX each day. And right now I mean, not right now, but until a while ago, we would have to translate every paper that was implemented in JAX to TensorFlow and everything that was implemented in PyTorch to TensorFlow, and that was pretty hard. And now at least the new papers in JAX, we can pretty much just grab the code and test it in our code base to see how well it plays with stuff. And all of that means that experimentation is now much easier, coding is much easier, and the modeling team is happy. And pass the slide, please. Okay. Now we also see that data parallelism with PMAP is very easy. It's pretty much plug and play. We have PJIT and XMAP, which Wang showed, which allows us to do sharding again very easily, almost plug and play. This one is slightly more complex, but again, it's much easier than what we have with TensorFlow or even PyTorch. We have a much better integration with XLA and with TPUs, which will help us in general get this better core utilization, which will reduce the communication costs considerably. But all of those things, they're really amazing. But the thing is, okay, what are we losing? And in fact, we're not losing much, because with JAX UTF, we can still use all of our pipeline, all of our old code base for serving models. So we are getting the benefits of a better way to represent our ideas while still having all of the amazing TensorFlow serving ecosystem. And there's just great support. We have the TPU chat where the JAX and Flax folks are always answering any questions we have. And all of that ends up making the Megazord team happy. And now Sid will show you a small proof of concept of using JAX and how you do break down models for pipelining.
Yeah. So this is really a toy example. I know everyone participating in this community, even they're getting a V38. So if you wanted to do this pipeline parallelism, or even just splitting model across devices, just wanted to show a toy example for representation purposes. It works, but we're just working with V38 under the pretense of like working with multiple devices. So let's just see how that looks, and it's going to be nice. Okay. Yeah. Can you guys see this? And should I just zoom in, or is this fine? Okay.
I think it would be great if you could zoom in just a bit. Perfect.
Is this better?
Yeah. Thanks.
Okay. All right. So with JAX and Flax, it's really easy to kind of emulate this distributed model behavior, and that's what we're going to look at right now. And even when I was writing this toy notebook, I was surprised at how simple it really was to kind of get this example going. So let's take a look. And firstly, it's just the normal imports. You import Flax, and Flax is our neural network module, and JAX and OptAX. We are using OptAX for our optimization. Can we get a link to the notebook? Sure, I'll share it right after this demonstration. And with H params, you just set up the learning rate, batch size, hidden size, and all of these things. And for the number of model partitions. So what we're doing here is we're trying to split up 6 layers into 3 devices. So each device has 2 layers each. Keep in mind that we're still using a V38, but I'm just using this for representational purposes, where I'm referring to multiple devices. So you'll see things will get clearer in a bit, but basically you have 3 model partitions and 6 layers in total, but spread across 3 devices with 2 layers each on each device. And you're kind of loading this MNIST data set for classification and the model class. I mean, Flax actually provides an MLP, but I'm just writing this out and just to be more explicit. So your MLP is a data class again, because NN.modules are, and your defining the number of layers, and in the call function, you're basically defining the layer as well as calling it with the compact decorator, which really makes the code simpler to read and use. And yeah, unless it's the last layer, you want to like have a dense layer and create an optimizer, use add-in, and you want to initialize your optimizer state and optimizer update functions. You want to return that, and that's all optax. And in the setup function, you're basically returning the model parameters and the optimizer states and updates associated with that network. And what network is here. So firstly, we set up a distributed model. So there are 3 partitions, and for each partition, we create a new network, and that's the MLP. And we create this network, get the optimizer states, updates, and like the parameters, and maintain that in a list. And you also set up a single model. We are setting up a single model because we want to kind of benchmark this distributed model with a single model. And by single model, I mean, since in the distributed model, you have 6 layers spread across 3 devices, the single model is just 6 layers as a single model, just to kind of benchmark it, make sure that there's nothing going wrong. And this is all general stuff. You standardize your data, and you have your metrics function. And okay, for the distributed network, you have forward and backward functions. And we need 2 separate functions, because for the forward function, it's just as simple as calling the network.apply function that your Flax module has. And the backward function actually needs to call network.apply again, because you have multiple batches that you're piping through these partitions, and the activations are not cached. So what you want to do is reconstruct those activations and then do the backward propagation. And because we are representing these 3 partitions as 3 devices, you need to take the output gradients from the loss and get it to the third device. And third device returns the activation gradients with respect to activations again, which need to be sent to the second device. And the second device needs to look at these gradients and needs to look at the activations that were produced by the current batch and reproduce the gradients within those partitions. Hopefully that makes sense what I'm saying. But in TensorFlow, what you would do is you would call tf.gradients with an argument that's referred to as output gradients. So you would take output gradients and pass it to tf.gradients. And with JAX, you have VJP that really simplifies things. And what it returns is the activations, the output of the network.apply, which is the activations, and the VJP function itself. And the VJP function, once you pass the output gradients, you get the gradients with respect to the parameters in that partition, and the gradients that you need to send to the previous partition. And so you return all of these things, and you define the loss function. That's all the normal stuff. And now here you're defining kind of the activation caches, and you're calling forward functions. And jax.value.grad, kind of you're just differentiating the cross entropy loss and getting the output gradient. And this is basically the backward pass. So you're calling backward, and all of this is handled in the backward function we saw earlier, where the output gradients are just being chained together, and they're being sent across all the partitions. And by indexing the right partition, you can just apply your updates locally to each partition once you have the gradients ready for the parameters with the gradients with respect to those parameters in each partition. And the single model train is basically training this 6-layer single model like in the just simpler JAX way. You call just a value and grad, and you call it on the loss function, which is just calling an apply, and you apply updates. It's as simple as that. For distributed model, because we needed to reconstruct the activations and handle the gradient computation, we needed like a backward function, but for single model, we don't. And this is all just the normal training loop stuff where you report the metrics, evaluate on the test set, etc. And you can see that as you train, you basically have very similar performance for distributed model and the single model. So that kind of ensures that there's no bugs here, there's nothing going wrong, and it's So this is just a super short collab that kind of emulates this distributed model setting. And I think it really drives home like how easy it is to write things in JAX and Flax and implement pipeline parallelism. Yes, the backward passes are done sequentially across partitions. So partition 3 takes care of it, then partition 2, then partition 1. Yes. And so, yeah, that's all we have for you today. And thanks for listening to the talk. And by the way, we are hiring. So if you're interested in joining us, you should shoot us an email. And there's also a Lever page that you can find on the website. And thank you.
Awesome. Thanks so much. Yeah, cool to see what you're working on at Cohere. And you just answered the last question in the chat. And we have, I think, 1 or 2 more more general questions. Let's have a quick look. I think 2 related questions, maybe just very generally. What is the tech stack that you're using right now at Cohere, and which multiprocessing libraries in particular?
Joanna, are you taking that?
Yeah. So yeah, we have an in-house data scraper and data filtration method. So it's a Cohere text, but yeah, it's like a web scrape text that is filtered on the toxicity, and yeah, and it's just a bit more of a data, like a pipeline. But yeah, it's like a web scraped in-house data for us. And multiprocessing library is the regular Python multiprocessing library that's got evolved to the array. And I think I missed one question about like the gradient accumulation and the sink. So we use something very similar to Hogwild. Let me actually post it here. Yeah, so we will have like a call that asks each partition to sync on the sync, which means that just apply the accumulated gradients, and yeah.
Cool. Yeah, a lot of people asked if it's somehow possible to share the collab and maybe the slides possible.
Yeah, I'll be putting the link in the chat right now. Just give me like a few seconds.
Mm-hmm. And let's see, there's one question. If you have some sort of time-based or let me read that TikTok clock dynamics for syncing gradients before accumulation, and the guess is if you're using Ray for this.
Yes, yes, this is the gradient accumulation and like the sync part. We can use Hogwild, but if like Hogwild is like hard to implement, what you can do is you can just count the number of micro batches, and so when you're done with like the full batch, then you can you can implement it so that it applies the gradients at that point. So it doesn't really have to be time-based, I think. Yes, and there were questions for Sid about the backward passes. This is the part where we implement gpipe. So in real life, we would actually place each photo partition to be in separate processes. So it doesn't necessarily mean it has to be executed sequentially. So João, do you want to answer?
Yeah. I think you answered the backward pass question. And which resources helped you people learn JAX Flax when you. So I really want to emphasize how amazing the support for JAX and Flax is. And we were talking to the Flax team the other day, and we really got insights into. They really helped us choose between, okay, do you want to use PJET or do you want to use XMAP, or what kind of like how would you go about JAX, and any kind of debugging issues. They've been super responsive and helpful. So I think, and the JAX docs are amazing. That I wouldn't be exaggerating if I said if it's the best docs for like machine learning based frameworks for JAX. And and we're really happy with the support we've been getting on that end. So yeah.
Yeah, some more specific points. I guess there's the JAX 101 series of tutorials by DeepMind folks. It's in the JAX documentation. And for Flax specifically, well, Flax has some pretty nice documentations and the how-tos showing how to use more advanced features. So I think these are the main sources that like would help you hit the ground running.